Epic. Epic! Epic Stat Tool 1 Speedruns of Statistics! Brian Stevens! Versus Chapter 13! Wow, that's a lot of content! Begin!
Chapter 13 has two parts to it. First, we have the sampling distribution for the sample proportion, and next we have confidence intervals for the true proportion. Now you'll notice here that we need to understand the difference between populations and samples. So when you look at the first one right here, we're actually talking about starting off with a population. And what does this mean? Well, when we talk about sampling distributions, maybe we work at a factory and we know 20% of our M&Ms are blue. So this means we know the truth for a population, and that would make this P right here. P is the truth for a population, and we're asking what might we see in a sample. But for the second part of the chapter, we're doing it in reverse. In the second part of the chapter, maybe we work at a factory where we don't know at this factory what the truth is for the true proportion of blue M&Ms. So in this instance, we're asking from a sample, what is the truth? And so here we have a sample proportion, and we're going backwards to understand the population. And this is a lot of times how it works, where you don't know the truth, so you're trying to understand what P is. But in the first part, we know the truth, so we're asking what could happen in a sample. So there's a key difference between when using a sampling distribution to understand what we could see in a sample, where you're going from the population to a sample for the first part right here, or in the second part, where we have a confidence interval to ask what might we see in the population, kind of some key concepts right there. And that's what we're talking about when we're talking about P hat versus P. So P hat, some instances of P hat would be, you go out and talk to, let's say, 100 students. And in this sample of 100 students, 60 of them are in state. So this would be an example of P hat right here, because X over N is going to solve for P hat. And you would get right here that this is equal to P hat of 0.60. So this is 60% of students in your sample. So note that whenever you have P hat will always be relative to a sample size. That's a good way to know that you have P hat versus you have P. Now, what is P then? P is the truth. If you were to go to the UT registrar and ask them what percent of students are in state, you would not have P hat anymore, you would have P. Because from the UT registrar, they would know, and this isn't from a sample, they would know maybe 68% of students are in state, and that's just a guess, but we'll go with it for the moment here. But they would know the truth, and this is for all students. So whenever you have P right here, P is for the population, so P is going to be for the population, where P hat is for the sample, and you'll always see a sample size right there. So kind of make sure you know the difference here, that P is the truth for a population. We have all the data from all individuals, where P hat is going to be relative to a sample size. So when we're talking about how to know, to identify what a success is, we were covering that just a moment ago with samples. What is a success? Well, you might be like, well, what does it mean to be successful? That's not what we're talking about right here. We're talking about X. A success is going to be X. So we denote success with X. And in our previous example, we had 60 successes out of a sample size of 100. And this is how we solve for P hat. So X over N right here, X over N equals P hat. And you can solve for the sample proportion. So that's how many successes we saw in a sample of a certain size. Have a general understanding of sampling distributions for a proportion. Now this is where it starts to get a little bit more complex. The sampling distribution for the sample proportion is a theoretical idea. And what does that mean? Well, we don't really know what could happen, but we have an idea what might happen when we do this. If we know, let's say we know that 70% of students at UT are in state. So we know the truth that 70% of students are in state. We would get here, the truth is 70%. And that means we would expect, so read the mu right here, I would expect when I take a sample, that's what the P hat represents, to see 70%, which is P right there. Very right here at the center, the direct center of this curve is 70%. And just think about this. If 70% of students are in state, if you took a sample, then on average, because that's the average sample, you would see this in your average sample. We'll go further in detail here in a little bit, talking about what would be unusual. But this sampling distribution right here is theoretically what could happen when you take samples. and the variation will tell us what we would expect. But all of these dots I'm drawing right here are different samples we could take. We'll have a sample size associated with this. But a sampling distribution is saying, theoretically, if you go out and take a sample of students, what should you see if 70% of them are in-state students? So let's find out more about that as we go through this speed run right here. So we have an idea what a sampling distribution is. It's a theoretical idea of what could happen when we go out and take a sample with known quantities, like we know the truth of the population. So now we need to know how to get the mean and the standard deviation of both of these right here, and we've already started this. Let's go back down to our notes right here. Going back down to the notes, you can see we already have the mean of the distribution. And what does this say right here? Well, this says, given 70% of students are in state, which is what we're saying. The truth is that 70% of students are in state. We ask student, are you in state or not in state? And this is the truth for everybody. UT registrar knows this. Then if we took a sample, on average, the mean of a sampling distribution, what we would see in a sample, is expected to be P. So literally you're just taking this right here and plugging in 70% right here. So the mean of the distribution is P, and that's what we have. So I'm going to bring that back to the notation we see, so we can just keep that right there. But you can also see this right here. Now, the standard deviation is going to be a little bit more complicated of a formula, and this is just the variation in what we'd see in samples. And this is going to be, let's move this down a little bit further over here. This is going to be P times Q over N square root. P times Q over N, and it's square root of the whole thing. P times Q over N square root. And when you solve this out, make sure to carry your decimals. I just type it all into the calculator. I'm going to write out the formula right here and what it equals to. So this is going to be equal to square root of 0.7 times 0.3 over square root. Let's say we talk to, we need to say how many students we're going to talk to, 100 students. That's just our sample size. And now this whole thing right here, let's solve it. Here we go with the calculator. Let's go here with P times Q over N. And then we do that and we square root it. So this is a standard deviation of about 0.046. We're going to round it for the moment right here. 0.046. 0.046. So there we are with the standard deviation for our sampling distribution of the sample proportion. And this tells us the variation we might expect to see. So the variation we expect to see is going to be about 4.6%. So now when we go up right here, we're going to go up 1, 2, 3 standard deviations, and we'll do some color coding here in a second. But this is showing us what we would expect to see with a mean of 70%. There's the mean right here. This is all the mean being calculated. And a standard deviation, which is the distances right here of the following. So here's the standard deviation for the distribution. There's all the calculations. And the standard deviation is the variation we'd expect to see. Because we won't see 70% in every single sample. What we could see within one standard deviation is going to be 74.6%. We're just adding the number right there. We're adding that point of that 4.6. Or we could expect 2 standard deviations up, not that unusual, 0.792. So if you're wondering how I'm getting these numbers right here, I'm just taking the rounded version. Let's use our rounded version right now. And let's just add that to 70. So here we go. We'll take 70, and then we'll add to it the standard deviation, and then we'll add to it again. And so here we go, 70 plus this right here, plus this right here, and now we have our number right there. We'll go plus one more time, and we get 83.8%. Now this would be very unusual. This is very high, 83.8% right there. Now we can go down the standard deviations to complete the curve. So let's put this right over here and just go down standard deviations. So we need to start at 70, and now we need to subtract the standard deviation we calculated. You can see right there in the corner, and we got 65.4, so 0.654. And then we're going to subtract the standard deviation again, 60.8%, 0.68. There we go, 60.8%, and we subtract one more standard deviation. Now, one thing I always suggest doing whenever you draw out this curve, right here, put your z-scores below it. The z-scores are going to tell you how many standard deviations something is above or below the mean. And we have made an excellent drawing right here to help us out. This is what I'd be doing on the test after finding the mean and the standard deviation. And what does this all mean now? Well, if I went out and speak to 100 students, because that's my sample size, if I speak to 100 students, I'd expect 70% of them to be in-state students because that's the truth. But then if I saw around, 65%, well, that's a little less than one z-score below. And so that would not be that unusual. 65% would be somewhere here, and that's not that unusual. That's kind of within the bounds of normality. But if I saw down here at about like 57%, well, that's going to start to get very unusual because that's more than 2 standard deviations above or below the mean. So when are things unusual? Well, things are unusual when they're outside about this bounds because this represents the middle 95% of possibilities via the empirical rule right there. So this lets us see what we would expect. Imagine you went out and talked to 100 students. Would it be unusual if 72 of them were in-state? And the answer would be no. You'd be right about here. And with 72% of them in-state, that would be a very probable event, or 72% of them or more, that'd be very likely to occur. And that's what we're doing when we calculate the mean and the standard deviation. Now, the shape of this distribution, you'll notice, is normal. So when is it normal? Well, it's normal when we meet the conditions. So the conditions you need to have are going to be the following. Once again, we've got here random. Condition 1 is random. What does that mean? These students I speak to need to be randomly selected. So I need to make sure the question says something like, I randomly talk to UT students, and then we've met the randomization condition. Of course, random is a little more complicated than that, but usually we try to make it very clear that we randomly selected the students. And if we don't make that clear, make sure to mark that. So we need to randomly select the observations. What does the 10% condition mean? This is the one people usually get confused on, and it's less than 10% of the population needs to be sampled. So are my 100 students I selected less than 10% of all UT students? And I would definitely say yes. 100 students is less than 10% of all UT students. This condition right here is a little bit complicated. Not going to go into great detail right now, but it has to deal with sampling finite populations and the errors that can occur by oversampling. That's kind of a little more complicated than we need to go. The best thing to do right now is to remember, sample less than 10% of the population to meet the condition. 100 students is less than 10% of all UT students. There's like 30,000 UT students. 100 students is less than 10%. As long as we sample less than 3,000 students, we're sampling less than 10% of UT students. The success failure condition for this one is going to be found via NP greater than or equal to 10. And also we need NQ greater than or equal to 10. And so how would we find these? Well, NP, remember we sampled 100 students and we expect 70% of them to be in-state. So that's going to be 70 students we would expect. So this is how many we expect to be in-state, and this is how many we expect to not be in-state. So with these numbers right here, we have now found that both of these are greater than or equal to 10. So we meet the condition right here because we have at least 10 successes and at least 10 failures. Now, what's the whole point of meeting these conditions? The whole point of meeting these conditions is that the distribution's normal. So by meeting the random, the 10%, and the success failure condition, we now have the ability to draw out this curve and use the normal techniques we're using right here. So next we see be able to use the 68, 95, 99.7 rule to figure out some probabilities. Now we can give you pictures via the David M. Lane, or we can have you draw it and try to figure things out. A lot of times people are wondering, how would we know the answer to a question like, what is the probability that 75% or more students are in-state in the sample? So we'll write this question right here. We'll just draw it out so we can see it. And here's what the probability would look like. And take a moment right here to see if you could figure out what this probability would be. What if you were presented with two choices? You're given the choice of either, and we'll do some colors right here. You're given the choice of A, the probability is going to be equal to 18%, or B, the probability is equal to 15%. And so which of these choices would you pick? Would you pick 18% or 15%? And we don't need the David M. Lane to solve this. We can actually solve it using the empirical rule. So we're going to erase a little bit of what's on this curve right now, just to be able to draw on here and make it nice and clear. So let's go right here and do the following. 68, 95, 99.7. And I encourage you to check back on the Chapter 5 speed run to remember how to use this. If we have 68% right here, well, then that means total outside is going to be what? If 68 is inside, then total outside is 32. 68 inside, 32 total outside, which means 16% on either one of these. So what does this actually mean that there's 16% in either one of these tails? That means above here is 16%. And look at the area I've shaded. If you notice, that is 16% above there, and the area that is blue is less than 16%. So that makes the answer for this question 15%. We can offer you pictures. There's a lot of ways to do these questions where we might show you David M. Lane pictures, but we could also have you use the empirical rule. And between 18 and 15% right here, the only choice that it could be is 15%, because that blue shaded area has to be less than 16% using the empirical rule. And the empirical rule is really great because we can use it anytime. We can always remember the 68, 95, 99.7 rule, and those are relative to z-scores. So be able to use the empirical rule. We got it. We've done that one. Let's take a look at the next one right here. Meaning of confidence. We've now gone to confidence intervals. So what does it mean to be confident? Let's go to a new page right here and start talking about confidence intervals. So when we have confidence intervals, it actually brings us back to the law of large numbers. If we make a whole bunch of confidence intervals, and we should be able to make them kind of quickly. Let's copy one. I can copy these. Here's a whole bunch of confidence intervals being created. When we create confidence intervals, it's not about one interval containing the truth. Sure, we'll put these up here. It's about in the long run, that if we have right here the truth would be contained in, if these are 95% confidence intervals, 95% of 95% confidence intervals are expected to contain the truth. So we kept making more and more and more intervals, and that saying right there is very important. Oh, we've now have less confidence intervals containing the truth. 95% of 95% confidence intervals are expected to contain truth. So 95% of 95% confidence intervals are expected to contain the truth. This goes back to law of large numbers, where we are talking about the long run probability of viewing this. So the law of large numbers states that in the long run, we will see the true probability of an event. So if we keep making confidence intervals, 95% of 95% confidence intervals are expected to contain the truth. And just think about this. Maybe you have a friend. We all have a friend. So you have a friend, and your friend says, I will show up to your house between 4 p.m. and 5 p.m. And they say, I am 95% confident. So the friend says, I'll show up between 4 p.m. to 5 p.m. and I'm 95% confident. So maybe today they show up at 5:02, and you say, wait a minute, you said you would show up between 4 and 5 p.m. When you actually showed up was outside the interval. And they said, well, I was only 95% confident because every once in a while I'm outside that range because, to be 100% confident, I'll say, I'll show up when I show up, which is true. I'll show up when I show up if I show up. We don't really do 100% confidence intervals because you'd have to cover all possible values. It's not just something we do in statistics. We give a range of probabilities that in the long run, these intervals would be expected to keep the interval, have the interval containing it that percentage of the time. So we'll talk more about your friend here in a moment and them showing up maybe between 4 and 5 p.m. But if they said, I'm 95% confident, then 95% of the time they told you they would show up in this interval, they'd show up within that interval 95% of the time. It's not about one time they're going to show up. It's about in the long run if they kept showing up with that interval. So we go back to the conditions again, and the conditions are super important right here to understand if we can use a confidence interval. These are the exact same conditions, but with one small change. The only change for this chapter right here, we'll bring it back down because we just need to bring these down here. Let's bring them down because it's going to work if we just copy paste. Come on, here we go. So we're going to make these a little bit smaller. There we go, and put them right here. And all we need to change for this chapter for the conditions, the only thing we need to change is going to be NP hat, NQ hat. Because in this chapter here, we do not have the truth. For the success-failure condition, we only have what we observe in a sample. So for the success-failure condition, we only have what we observe in a sample. So you need to look at your NP hat, your NQ hat. And how does that work? Well, in an example problem, you might be given something like, let's say we want to make a 95% confidence interval. Let's increase font size right here. Make a 95% confidence interval for the true proportion of students who like Taco Bell, favorite restaurant ever. So with Taco Bell, we would say we speak to 100 students and find that 80 of them like Taco Bell. Use a 95% confidence roll and check the conditions first. So let's take a look at this confidence roll and use the notation. Practice on notation right here. So the first thing we see is we have 95% confidence, and this is what our z-score is going to be with. So when we do this, this is just like our 68, 95, 99.7 rule, but we do a more exact z-score that carries the decimals of 1.96. 95 is actually a z-score of 1.96. 68 is very close to 1. 95 is close to 2, 1.96 to be exact. And 99.7 is a z-score of 3. So 68, 1, 95, about 2, and then 99.7, 3. Next, we have more notation to practice. We speak to 100 students. Make sure to practice the notation. This is going to be your sample size right here, which is how many students we speak to. This is the one students usually forget. This right here is how many successes, which we covered earlier. The amount of successes we have is going to be x. So now from x over n, we can get p hat right here. So p hat is equal to 80 over 100. Nice and easy mathematics today. And we can get here that p hat is equal to 0.80. Now, as soon as you find p hat, you need to find q hat. Q hat is just going to be 1 minus p hat. So q hat equals 1 minus p hat. And that works the same for q. So all we're doing right here, whenever you find p hat and q hat, make sure they add up to 1. So your p hat and your q hat should add up to 1. And I think we have all the notation we need now. So now you're wondering about the conditions. Well, make sure you speak to 100 random students. We didn't put that in here, but we should say 100 random students. Are 100 students less than 10% of the whole UT population? Yes, because there's 30,000 students. And then do we have at least 10 successes, at least 10 failures? And we do, because you'll notice here that the amount of successes we have is going to be NP hat, which is going to be 100 times 0.80. And interestingly enough, this is x. So we actually have at least 10 successes. And then the amount of failures we have is going to be NQ hat. So let's go ahead and put NQ hat in here, which is just going to be the other side of it. It's how many people did not like Taco Bell. I have no idea why. Taco Bell's awesome. And if you disagree, go try some nacho fries. And there's our NQ hat right there. So that's how many successes and failures we have, and we meet the condition because there is at least 10 for each of them. So make sure to review these conditions right here. Random, 10%, and at least 10 successes, at least 10 failures. And the 10% is less than 10% of the population is sampled. Margin of error is a very, very, very important concept. The margin of error is used for all confidence intervals, and let's write some equations for it to help us out right here. When we talk about the margin of error needs to be viewed conceptually. The margin of error looks like this. It is just a plus or minus on an interval. So the margin of error is going to go up a certain amount and down a certain amount from the center. So you have the center of an interval, the upper of an interval, and the lower of an interval. And then you have plus a margin of error, and you have minus a margin of error. So let's think about this for a moment right here and put it in context of our friend. So if your friend says they will show up between 4 and 5, your friend says, I will show up between 4 and 5, then what would the center of that interval be? So your friend says between 4 and 5. Well, 4 to 5, the center of that interval is 4.5. And mathematically speaking, in terms of hours, that is 4:30. So we can convert that right here to a time of 4:30. And now you would say plus or minus 30 minutes right here, because we're talking in terms of hours. So this is just some conceptual ideas right here that we understand if we're doing a confidence interval, we can find the center of it by averaging the two values. So let's write that down real quick. If you just average the upper and the lower like we did right there, so the upper plus the lower divided by 2 is equal to the center. But what do you notice about the margin of error? Just look at the margin of error and look at it this way. The margin of error is what? The length of the interval. The margin of error is going to be half the length of the interval. So to find the length of the interval, we can do the upper minus the lower. Let's go here to upper minus lower, which is just how far those two numbers are apart, and then divide that by 2 to get the margin of error. So the margin of error right here is going to be equal to half the length of the interval. The length of the interval is the distance from the upper to the lower, like the range of the interval. So now that we have this, let's look at our Taco Bell example and see if it applies to this concept. So the next concept we are covering right here is going to be how standard error is related to standard deviation for proportions. So let's go ahead and solve out this interval right here and calculate the standard error. The standard error is just like the standard deviation, but it's for our confidence interval. It is just the variation. And let's calculate the standard error. So when we look at our confidence interval right here for the Taco Bell example, we'll remove the checking of conditions right here. And Q hat is just going to be equal to that right here. So we know P hat, we know Q hat, and now let's solve our interval. There's Q hat right there. So the interval is going to be P hat plus or minus Z, and then we times it by P hat Q hat over N square root. Very similar to the last equation. P hat over Q hat N square root. And this portion right here is the standard error. This is the standard error for the confidence interval. And the Z-score gives you how confident you are. Take notice that the Z-score up here is relative to the 95% confidence. And here, the P-hat is the very center of the interval. So this P-hat is the center. And then everything to the right of it, everything from here over is the margin of error. So we have the margin of error from the plus or minus over. So when we're solving this, we just need to put in the numbers we are given. We are usually given the Z-score, especially if we're doing a test problem that says a 98% confidence or a 99% confidence. So let's go ahead and solve in the numbers. So with this, we're going to erase the previous parts and just leave our P hat and Q hat over here so we can see them. So P hat was equal to 0.80 and Q hat was equal to 0.20. And now we have 0.80 plus or minus 1.96 square root 0.8 times 0.2 over 100. Be very careful as you put this into your calculator. Let's check this out right here. So here we are with our calculator. Let's get it nice and situated on the screen right here so we're not blocking anything. There's the calculator, and it'll go right over there. Perfect. So I always start with the inside portion right here, 0.8 times 0.2. There's that times together, divided by 100. We've now completed this portion. We'll square root now and times it by 1.96. And we have now found the margin of error. The margin of error for this interval is 0.0784. So what I do now to help out is I'm just going to take and rewrite this interval right here as 0.80 plus or minus 0.0784. And now we can see that the interval would go all the way up and all the way down to, let's solve right here. So we're going to copy that, 0.80 plus, there's the upper of the interval, the top portion of the interval, and 8784. And now let's find the lower of the interval, the lower portion. And so we'll go 0.80 minus, and there we go with the lower, just adding and subtracting. 0.72, and that should be 1/6 at the end. Let's double check. Yep. And so what does this mean? Well, this interval right here, which has a margin of error of the following, this is the margin of error, and this is the center of the interval right here. We are saying I am 95% confident the true proportion of students who like Taco Bell is contained in the interval 72.16% to 87.84, or you could treat it as 0.7216 to 0.8784. We're trying to estimate the truth for all students from a sample of 100 students. And just like, and I'm going to do a rounded version of this, 72 and 88, just like our previous interval, let's put these numbers in here. Notice what we have. If we go right here and put 72%, and 88%, let's change colors on this a little bit right here. So if we go right here and go 72 and 88, could we figure out the same sort of metrics? 72%, 88%. What is the center of this interval? What is the margin of error of this interval? So take a moment, think about this for a moment. What is the very center of this interval? What is the margin of error? And you should get 80% is at the center, because if you average together those two numbers, 72 and 88, 80 is at the center. And then the plus or minus on this interval is this. This is why I think memorizing these equations right here is not so important, because as long as you understand theoretically how a confidence interval works, you're actually doing this where you're averaging together the two numbers to find the center of the interval. Because just remember, you have 72 and 88 just average them together to find the center. And then if you're thinking about the margin of error, it's going to be the plus or minus on the interval, how much ever you're going up or how much ever you're going down from the middle of the interval. So we just used our interval here that we created from the Taco Bell question to do the same thing. We did a slightly rounded version of it to make it easier to see. That is what the margin of error is. And we're not saying that's what the truth will be. And we're saying, yeah, probably 95% of the time our interval would contain the truth. When it comes to critical values, there's a whole ton of them. Just to mention some briefly right here, you will need to know how to look at output, but we could just give you the following right here. Like, let's do a drawing of a critical value. And so we'll go to a new page right here. And if we were to give you the following, what could this be used for right here? So here is the way you could see a drawing, and we would go right here with the center. And what would this be? You'd probably get something close to about this right here. And actually, it should be a little more over. Pretty good right there. And here's what would be shaded. And it would say something like Z of 1.2816. And you would see here that the percent shaded between is going to be 80%. And this would be the Z-score for an 80% confidence interval. So we're just going to say 0.80. But we'll give you pictures of things like this, and you would then need to know how to use this as a confidence interval Z-score. And we want to always look at confidence intervals at the percent between, the shaded area between, and that is the Z-score for an 80%. Which brings us to some important topics. When you think about the shading on the interval, if you were to increase the shading, if it were to get wider or smaller, well, then that's going to change the Z-score. So if we think about how this works right here with Z-scores, if you go to a 90% confidence interval, a 90% confidence interval, and you do not need to memorize these, is going to be 1.6455. So it changed colors on me right there. A 90% is going to be 1.6449, and that is where a 90% is, where we shade more of the curve. If we go to a 95% confidence interval, it's 1.96, very close to 2. So you can notice as we increase the confidence, this will be one of our last concepts, the precision is going to get smaller. The interval is getting wider and wider as we increase our confidence level. So this is now a 95% confidence interval. And you'll notice you just keep going out further and further and further as you get more and more confidence. And this is a key concept, that as you get more confident, you're going to see the interval get less precise. So this is a big trade-off right here between the certainty and the precision. Big trade-off of the uncertainty and the precision. Finally, be able to calculate a confidence interval with the aid of a formula sheet. We've been going over the formula sheet a lot in this video, so make sure to check that out. And now we will do one confidence interval right here. Let's take a look. Here's a confidence interval, and let's take a look at it. With this, we have created some jump output, and we are looking at a 95% confidence interval to estimate the true proportion of votes we will get. And if you notice right here, these are the numbers of successes, 470 successes. That is a probability right here out of 1,000 voters that we spoke to of 47%, or a proportion of 0.47. And the lower bound of this confidence interval is 0.43924, and the upper bound of this confidence interval is 0.50099. So I am 95% confident the true proportion of votes I will get is contained in the interval about 44% to 50.09%. And what does this mean? Well, if you're taking samples of people, then you're saying maybe on election day, this will be the proportion of votes I get, somewhere between about 44 to 50%, if we just round the numbers nicely right there. Take a moment right now, see if you can figure out the margin of error for this and all that good stuff. But here's jump output. Here's how it looks. And these numbers right here, this lower and this upper, is the same thing we've been calculating when you look at these theoretical problems right here. We'll put it on the screen at the same time. But that lower and that upper for the interval is going to be the lower number down here and the upper number right here. And then this probability right here is the middle number. So that 47% is the same middle number you see here. This lower is going to be right there, and this upper is right here, and then there's the percent confident, and that is how to read the jump output. With that, under 34 minutes, this takes about 3 hours to cover. Great work, great review, and email me if you have any questions.